We know that the x-intercepts of a graph occur when the function is equal to 0. So what we're really looking to see is when the function a sub 0 x to the 11th plus a sub 1 x to the 10th plus ... all the way down to a sub 11 equals 0. And we only want real solutions to this polynomial equation because complex and imaginary solutions don't correspond to x-intercepts. I think it's not too difficult to see that m, which is the most number of x-intercepts that this graph could have, which is the most number of real solutions that this equation can have, has to be equal to 11. We know that an 11th degree polynomial can potentially be factored into 11 linear factors, each of which has a real number solution. And so long as these factors are different, those give us 11 different solutions, which gives us 11 different x-intercepts. If you wanted to construct this polynomial, you actually could. You could say that this polynomial was x minus 1 times x minus 2 times x minus 3 all the way up to x minus 11 equals 0. If you went through and did all of the multiplication and expanded all of that, you would get an 11th degree polynomial with 11 distinct real solutions, which would give you 11 x-intercepts. So we can see fairly easily that m equals 11. The challenge is figuring out what the least number of x-intercepts that function could have, which corresponds to the least number of real solutions that this polynomial equation can have. Now, it's not possible for this equation to have 0 real solutions. And there's actually a couple of ways that we can see that. One of them involves a theorem called the complex conjugate root theorem, which says that if p is a polynomial with real coefficients and the complex number a plus bi is a root, then its conjugate a minus bi is also a root. Now, if it was possible to have no real solutions to this equation, to have no real roots, that means that all 11 roots would have to be complex numbers. But it's not possible for a polynomial with real coefficients to have an odd number of complex roots. So if we look at the 11 roots to this polynomial, at most 10 of them can be complex. And if that's the case, that means that we are stuck with one real root, which means n has to equal 1. The problem is asking for the sum m plus n. This would give us 11 plus 1, which is 12, and this is answer choice D. The other way to see that n equals 1 is by thinking about what the graph of the polynomial p of x might end up looking like. Since it's an odd degree polynomial, we don't know exactly what the graph will look like, but we know that the graphs of odd degree polynomial functions have end behavior where the left-hand side of the graph and the right-hand side of the graph end up moving in opposite directions. Specifically, if a naught is positive, then the left-hand side of the graph is going to go downward towards negative infinity, and the right-hand side of the graph is going to go upward towards positive infinity. Similarly, if a naught is a negative number, that's going to reverse things. The graph is going to go to the left up towards positive infinity, and to the right down towards negative infinity. But because the graphs of polynomial functions are continuous curves, we know that if the graph is going from negative infinity all the way up to positive infinity, or from positive infinity down to negative infinity, that graph has to cross the x-axis at least once. It might cross the x-axis more than once, giving us more than one x-intercept, but n is the least number of x-intercepts that we're going to have, and so we know that there's at least one, which also verifies that n equals 1, and in that case, m plus n is still 12, which is answer choice D.